Okay, on the one-dimensional walking in front of the motion detector on the lab, there's a question that's usually confuses people, and I want to show you how you can write out the details. And that's a big thing that we're learning. Once you get that, that's you're good to go with a lot of problem solving. You still have to work things out. But thinking physics, writing math, writing out the details. So we were given that the velocity versus time graph looked like this. And we were asked to graph position versus time. So the challenge is we need to think about the meaning. The meaning of the slope is different for these two. The meaning of graphical area is different. The meaning of the points is different. So you have to pause and really think slowly, and eventually you'll build up that speed. So what I'm going to do here, you don't have to. There are quick ways to do this. But let me do this carefully. If I'm confused, I need to slow it down and work it out. So one thing I can do is these are moments in time. I'm going to have to look carefully at these axes. So these timelines are lined up. Notice that that's not 1 second, it's 2 seconds, right?
Yeah.
So I've got 2 seconds, 4 seconds, 6 seconds, 8 seconds, and so on. The other thing that I can do is think about instants, states. And so I could label this state 1 right there, state 2, state 3 is right there, and state 4. So I can use good subscripts. Now I don't necessarily have to in this case, but I'll just show you how nicely that works out. So, oops, I've got all this stuff up here. Didn't want that up there yet. I'll talk it through. Okay. So, let's take a look. What do I have? So that's my mantra. What do I have? I know that the velocity is 1 meter per second. No, it's not. It's a half. Why do I know it's half? Oh, the 1's up here. So that's a common mistake. It's fine. So just don't jump to conclusions. Right here, this is 1. That's a half meter per second, and it's positive. So 1/2. Okay, so there's a place you can make a mistake if you go too fast. Just make sure you velocity is 1 meter per second. I also know that it's flat here, so that the v value is constant, which means I'm moving with a constant walk or a constant velocity. So since it's constant, since the velocity is constant, I can say, and so this is my way to justify it to the world and myself, since the velocity is not changing, then that's the same as the average velocity. And what's the average velocity? Oh, I got to tie all these things. I got to think this, and I got to write everything I know. Who knows what I'm going to use? If you're worried about what you're going to use and what you're not going to use, you're going to be thinking way too far ahead. Just see what you've got. Maybe I don't need this. So that's that. Now I've got delta x over delta t. But again, it helps to know what states you're looking at. In this case, I'd be looking not 1 to 2, because the velocity is 0. Velocity is 0, 1 to 2. Oh, that means I'm just staying still. Velocity is 0 means I'm staying still. So to here, I'm going to stand still. That's at 3 seconds. And if I look at my scale, I've got that at 1 meter. Okay, so I'm going to stay still for 3 seconds, but then from 2 to 3, so let me write that. 2 to 3, 2 to 3, that's equal to 1/2 meter per second. So I'm just thinking it through. And again, it doesn't matter the order. You don't have to memorize this. You just have to start writing, pulling out things from your toolbox. What do I know? Time from 2 to 3, 2 to 3, 2 seconds, 3 seconds. So I made this leap here, and I've got delta x over 3 seconds. I can just see that, so I'm gonna write that. And this is delta t from 2 to 3 is equal to 1/2 meter per second. So what else can I do with that? Well, I could multiply both sides by 3 seconds so that delta x from 2 to 3 is equal to 1/2 meter. I multiplied by 3 seconds, seconds went away, and oh, you see how I can make that mistake? So you don't want to be too quick, or you want to check yourself. I multiply by 3 and then seconds. So maybe I want to write that out, maybe I don't, but those mistakes can cost us. Okay, so my displacement from 2 to 3 is 3/2 of a meter. Now I could say, well, what's displacement? Let me write that out even more detailed. Well, displacement is x later minus x earlier. In this case, I've got x3 minus x2. And that's equal to 3/2 of a meter. What else do I know? That's what I keep asking myself. What do I know? What do I know? x2, oh, it stays at 1 meter. So x2 is 1 meter. And I've still got x3 hanging out here. I don't know what I'm doing. I'm just moving the puzzle pieces around. Oh, that means that x3 is equal to 3/2 of a meter. Add that to the other side, plus 1 meter, which is equal to 1/2 plus 1, 2.5 meters. So I end up at not 1, not 2, but 2.5 meters after those 3 seconds. 1, 2, 3 seconds. I am here. It's constant, so it's a straight line. Then I've got negative 1/2 meter per second over 3 seconds again, so I'm going to go the same distance. I could do it out again, or I could realize that I'm going to end up 1 second, 2 second, 3 second, come back to the same place, lining up the times, lining up the times. Now that's nice and careful. Now I want to show you one other thing. Graphical area on a velocity versus time is going to be delta x. If I'm looking at 2 to 3, that's v, which is a constant during that period. Delta t, 2 to 3. My v is 1/2 meter per second. My delta t from 2 to 3 is 3 seconds. And I'm back to the same answer that I got before. That is shown here as my delta x, but on this graph it shows from here to here. That's my delta x going up there in that time. I've gone up there. And you can do it down here, but it'd be a negative delta x. In this case, it's the same. It doesn't have to be. You just write it out. You don't have to do it in your head. I want to note that the slope on v versus t is, of course, change in v over change in t, or dv dt. It's the rate of change of velocity. Of course, that's the acceleration. One last little bit just to do this is I've drawn this graph here. So this is a good thing to be able to answer on an exam real quickly. Notice, I could ask you, does that show a change in direction? And it's tricky because in your head you go, well, what's the answer? Don't go there. Look at it and see what it says. And that's what the study is right now. You're doing lots of little exercises. Notice that this is v equals 0. This is positive v, which means the direction, and then this is the other way, negative. So in this case, notice I'm traveling in the positive direction. Let's say it's that way, but I'm going slower. My graph looks like it's going the other way, but that's not. This is v versus t. This would mean something entirely different on x versus t. So I've got it decreasing speed, but still going that way. And then I've got increasing speed, but still going that way. I never turn around here. So this is going fast, going slower, slower, now going faster and faster, but all in the positive direction. The only time I change direction is if I go from positive to negative, which means at some instant or time interval I have to have a zero velocity, or from negative direction to positive direction. So those are things to think about. Push yourself to exercise. Think about the meaning, and then here's a little practice. What would it mean if this was x versus t? And that would be x, x, and x. And so think those through, draw some, test each other, and hopefully that helps you to translate graph to meaning and meaning to graph. And of course we've got equations that tie it in too, so there's lots of ways, and you get it, but keep doing problems. Awesome.